The next speaker is Dominic Fu from Malaysia. Professor Dominic Fu is Professor of Process Design and Integration at the University of Nottingham, Malaysia. He is the founding director for the Center of Excellence for Green Technologies. His research interests are process integration and optimization for sustainability, process safety and environmental protection, and many more. I invite you to give your speech.
Thank you, Prof. Good morning, ladies and gentlemen. My name is Dominic Fu. Originated from this province called Hainan in China. That's where my grandpa, my grandma come from. 我中名是看得到叫福传义，符合的福传统传艺术的艺。I am very fortunate to be invited as one of the non-Chinese to be here to share with you a bit of the work that we have done in the past 10 years, particularly on CO2 reduction. And for the past 2 years, I've been traveling to China since COVID was over. I flew in every maybe 3 to 4 months once. Some of those trips were delayed trip since 2021. So every time I came in, there were people telling me that, oh, we need to achieve CO2 peak by 2030 and we need to get down to zero by 2060. They call this a double carbon mission, okay, for the Chinese country and government. So let me share a bit of what we have done in process integration. I understand that time is a little bit constrained here. I will try my best to deliver this within 30 minutes if possible, so that we have the next speaker before we go for lunch. I'll share with you some work that we have done in process integration from graphical, magnetic, and hybrid methods. Okay, this is what we call a subset of process system engineering. This technology called process integration introduced back 40 years ago. In the first place, many media has been telling us that, well, 2023 is the hottest year in history. Yes, for a short while this will be the record, but I'm pretty sure this will be hotter rather than hottest. Maybe sooner, later this year, this will be the next one that we call it 2024 will be the hottest. Then when it comes to 2025, it will be another hottest. In a nutshell, we have hotter and hotter and hotter and hotter rather than hottest. Whether you like it or not, this is having a high fever for the planet Earth that we are living. So some of you have heard that the first speaker will talk about planetary boundary. The one that is relevant for my discussion today is CO2 concentration. Back then, when this bunch of scientists introduced the planetary boundary, it was proposed that we should hit CO2 by climate change, which is the symptom that we describe. What we call the symptom for climate change. If you say that our virus for COVID is that little virus, the virus for this high fever sickness of the planet is CO2. Okay, unless we remove the what we call the virus away, I don't think we can cure the high fever of the planet Earth, unfortunately. When they proposed this boundary back in 2009, you can see that they say, oh, we should keep the CO2 concentration by 350, but that time it was already 387. It exceeded 400 by 2013, and this was the statistics 2 months ago when I shot it from the Killing Curve website. If you have not seen this yet, I encourage you to go and go to the internet and do a search. Every 2 weeks they will do updates. So the data shows that now we are approximately 420 plus. Okay, every few months it will go up and down a bit, but in general you can see that in the last 60 years it will go up and up and up and up. We hope that it will really reach the peak at 2030 and slowly go down. In fact, some scientists say that we should reach the peak by next year, 2025, or else we are preparing to move to Mars in 30 years. Okay? Right. Of course, everybody talk about Paris Agreement when we talked about climate change, but this was one of the most important COP event in the past 10 years. Every year they are doing this COP conference. Okay, last year it was in Dubai. This year I don't know where it's going to be. But most of the conferences in the past 10 years, not very significant. People will say that blah 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 blah, and that's it. Okay, the more important one is 2015, where we have the agreement that we should do our global effort to keep the global temperature rise by 2 Celsius and try to limit it by 1.5 Celsius. And if possible, we want to make use of all this technology. And by the way, this is called technology wages. It is a bit like the food, potato wages that you eat from all the fast food restaurants. And if you like to eat potato wages, you should also adapt technology wages to decarbonize whatever sectors. Okay. On the right hand side, you see a whole range of technologies that we should be adapted in order to get rid of our virus, which is CO2 from the atmosphere, so that we can cure the high fever sickness of the planet Earth. I'll go bit by bit to introduce how can we do this through system engineering techniques. Being a salesman, I tell you the best technique I will sell you is process integration. Of course, all the speakers will say their techniques are also the best. Okay, this is one of the best. Okay, people say that. Okay, this is something too new for those who have been working on this system engineering. Or I would say, if you come from chemical engineering background, you probably learn this for a few weeks in the undergraduates, where that's the first trend of process integration dedicated for heat recovery. Back in the 1970s, some gentlemen like Botolinov, Robin, they started this exchange synthesis. 1990s, Mohammed and his gang have started extended heat to mass exchange, trying to address pollution prevention problem. Then 1990s, we have Robin, who introduced automation and production supply chain by some Indian presses, Shinoy, and hydrogen pinch came into picture in the early of this century. And of course, there's property pinch by Mahmoud, and then 2007, Raymond and myself started something called carbon pinch in short. It is trying to address energy planning problem through CO2 limitation. Okay. These are some of the very established tools. Okay, as I said, if you come from chemical engineering, you learn some basic process integration methods. Okay, every now and then, people are using it to design plants. Almost 2/3 of the universities in the world introduce this to their undergraduate students. If you are generating about, let's say, 50,000 pinch studies in the universities globally. Okay, nothing new. Okay, but people are talking about how to make use of these techniques to address other problems apart from energy integration, energy recovery. In the process plants, we talk about how to reduce waste, how to reduce water, how to improve efficiency, how to improve throughput. Okay, through the use of some system engineering methods. Of course, process integration is one of those. Whether you like it or not, our industry, the chemical process industry, consumes approximately 1/3 of the world energy, and a big majority of this energy is actually fossil fuel. Okay, you can see the numbers over there. We have been teaching our students, our industry players, how to make better use of fossil fuels in the last century. Okay, switching to renewable is a trend. Okay, but it is not a solution to solve global problem. At least not now. Okay, probably 5-10 years from now, maybe it's possible. For those who have learned process integration, in the undergraduates, we talk about the plotting of temperature versus enthalpy diagram, like the two composite curves there, the overlapping region tell us how much energy we can recover, and we do the design of the exchanger network on the right hand side using the grid diagram. Standard method. Everybody do it, get the same answers. Everybody do it, achieve the same targets with the design, and that's the beauty about this technique. Okay, back then, 20 years ago, some consultant would tell the plant players, okay, pinch is very difficult. Okay, leave that job to us, we will solve your problem. Okay, as long as you pay us money, we will solve your problem. Okay, today we tell the engineers, you learn this in the undergraduate, go to the plant and do it yourself. Okay, you don't need any big consultants, okay, because it's not too difficult. Right, today we'll talk about how to, when we talk about energy recovery, what we actually do is to improve and use fuel efficiency. We are putting fossil fuels, generating steam, high pressure, low pressure steam, hot oil, all these energy utilities that we utilize in the plant. Once we design the system or the processes with process integration method or system engineering methods, we can get a high efficiency for the fossil fuel that we use. Okay, that's address one of those things, and this is in the low wages, low wage. You can see that it decarbonizes quite a bit of CO2. Okay, meaning that if you can improve the plant efficiency, you reduce CO2 directly. Okay, this was there for the past 4 decades, 4.5 decades ago. Okay, very, very established. Back then, when this technology was introduced, it was not meant for CO2 reduction. It was meant to reduce operating costs. So today, apart from operating costs, apart from profit margin improvement, we are talking CO2 reduction target as well. Okay, we address CO2 reduction indirectly through the improvement of fuel efficiency. Okay, now that was 1980s, 1990s. Those techniques are now very established. Now let me draw your attention to CO2 constraint planning. Okay, when we talk about CO2 constraint planning, we are talking about the allocation of resources, energy resources, can be in the form of fossil fuels like coal, natural gas, oil, can also be in the form of renewable energy. We want to allocate these energy resources to the sink. This energy sink can be in the form of countries, cities, sectors. Okay, can be economic sectors, can be geographical regions, can be a province, can be a country. As long as you define the needs of energy and you define the limits of the CO2. Okay, you are given a set of energy demand, or you can call it demand, you can call it a sink. Each of the demand requires some energy consumption, and that is the maximum limit of CO2. And obviously, this can be set. Okay, the country set overall target for entire region, different regions. For example, this Zhejiang province, you can have one target, and then you can have one target for every cities in Zhejiang. Okay, one Hangzhou, one Shaoxing, another one. So this is something that we need to set. But once we have that, we look at whatever energy sources that we have. Can be fossil fuel, can be renewables. Each of these sources have their availability, have their emission intensity per energy content, how much CO2 is releasing. And we are trying to identify what is the minimum CO2 neutral or low carbon sources. Okay, why do we need to minimize them? Whether you like it or not, solar, wind, all has their own limitation for now. Okay, you can't simply just replace all the fossil fuel with renewables because it's insufficient of use. The availability is still quite low. Okay, so we are still using fossil fuel. Okay, but most of the time we are transitioning to cleaner energy, for example, natural gas, and then try to phase off coal. So what we are trying to do now is to make use of renewables, or maybe you want to call nuclear is also renewable, up to you. What we are trying to do is to identify the targets of minimum renewables that we need to put in the system. For example, if you're plotting CO2 versus energy content diagram, this is what we call the energy planning inch diagram. The red lines are the different regions that require the energy, and the blue lines are all the energy sources that we have. Okay, how do we allocate them in order to get to the CO2 limits that we have targeted? Okay, there are two different versions of this diagram. Sometimes, if the diagram on the left is looking at the net zero sources, on the right hand side, this is low carbon source. Okay, when you have two diagrams plotted on this diagram, the overlapping region tells us how much energy can be allocated from the sources to the sink. The gap on the left is the amount of zero or low carbon source. On the right hand side, this is the extension of that, whatever excess. Okay, those are the dirty, okay, high intensity carbon sources that we need to phase out. Okay, we can close down the power plant, but we have to slowly plan it so that we close down in 3 years, 5 years, 10 years, so that we can secure a job for people. Okay, but once we know how much renewable we need to plan or construct in this region, then we can slowly close down the high intensity carbon sources. Again, using an example, this first paper that we produced in 2007, that was based on a case study in a country called Philippines, 2 or 3 hours from here. This Philippines has 3 different regions. You can see that in different colors. Each of these regions has its own energy demand, and each of them also has their CO2 emission limits. Okay, E1, E2, E3, E1 is this regions where the capital city of Manila is based. Okay, it has a higher energy demand, 1 million terajoule, and then the CO2 emission is about 20,000 tons. And if I divide the CO2 emission by energy, that gives us a carbon intensity. You can see that B1 requires lower carbon intensity versus it's a city center. Okay, those have more population. We want to have lower carbon intensity. B3, on the other hand, B3 all has its own energy requirement and carbon intensity. B3, for example, has a higher CO2 emission because this is a region which is less people. Okay, we can say that this region has less people, we can release more CO2. The city center should release less CO2. Okay, so what we need to do is to identify how much natural gas, oil, and coal that we should allocate to these B1, B2, B3, these three different regions by observing the limits that has been set by the country. Coal is usually the dirtiest. Okay, every terajoule is about 100 tons of CO2. Natural gas, we call it transitioning gas, half cleaner compared to coal. Oil is somewhere in the middle. All three are dirty. Okay, we try to use the less dirty one. Okay, and if possible, we want to use renewables energy. However, our availability of renewable energy is very, very low. My friend did an analysis. If the whole country of the Philippines are planted with coconut trees, and coconut trees, we have the highest rate, we can make biodiesel from coconut. Everybody live on the tree, still not sufficient to cater the needs of biodiesel in the country. The yield is too low. Okay? Every one of us will live on the tree, yet the coconut trees produce biomass that is still insufficient to use for the country. You get what I mean? The yield is quite low. So what we do now is to plot the CO2 versus energy content. B1, B2, B3 can be plotted such as increasing slope. It means that region B1 has a least lowest, okay, steepest is the D3. The leanest is D1. It means that D3 can release more CO2 compared to D1. The total energy required by these three regions is 2 million terajoule, and the total CO2 that can release is 100 million tons, okay, for these three regions. So there are two constraints here. Constraint number one, we need to supply the total energy of 2 million terajoule to these three regions. And each of these regions has their own CO2 emissions. When you add them together, we should not release more than 100 million tons of CO2. And we can achieve that using all these energy sources that we have. We start by plotting natural gas, oil, and coal. Okay, if you plot natural gas, oil, and coal, the total energy they have over there is 1.6 million, and the total CO2 is 135 approximately. This is a problem. Number one, energy security is a big issue. Okay, they require 2 million terajoule of energy, but availability is only 1.6 million. Okay, number two, they can only release 100 million tons of CO2, but at the moment they are releasing 135 tons of CO2. Okay, both are a problem. Okay, both are an issue. Okay, energy not sufficient and CO2 are more than what they have. So what they need to do is to plan production of renewable energy, and this cannot be done overnight. We need to have a long-term plan. So what we need to do is to shift the whole this red line is called a source composite curve. These are energy sources. We shift this source composite curve to the right-hand side, and until we reach below and to the right-hand side of the sink composite curve or the demand composite curve, so that you can see that it will fulfill the energy over there by putting in approximately 813 million, 1,000 terajoule of energy, and then the CO2 limit is 100. They can fulfill it up to here. Okay, and everything is stopped by this something called pinch, which is a bottleneck. Okay, this bottleneck stops us from using more fossil fuel. You need to have something like about 813,000 terajoule of renewable energy, or else the CO2 limit cannot be preserved for three different regions. Okay? Anything excess on the right-hand side, on the top right corner, that is excess of energy. That means coal power plant have to be slowly shut down. Okay? From approximately 60% of coal power plant have to be shut down so that we can still preserve the limits of CO2 that is set by the government. Okay, so doing this helps us to do energy planning. We know how much natural gas can be utilized. All natural gas can be utilized, all existing coal power plant can be utilized, but coal power plant can be shut down. Okay, approximately 60% of coal power plants need to be shut down. Okay? If we assume renewable energy does have a small carbon footprint, for example, we are using wind turbine, we are using solar panels, all these materials tend to be spoiled after 10 years. They will still, this waste dumping still release some CO2 in terms of long life cycle assessment. That means that we need to analyze it using this shifting of composite curve on this locus. That locus has a slope correspond to the emission of the renewables. Okay, you can see that we need to use a bit more renewables. Show it in the table form. If we assume no CO2 coming out from renewable energy, you only need 813 terajoule of 1,000 terajoule of energy. But if you assume that this renewable energy do have a bit of CO2, we need to have a bit more, okay, 1 million terajoule of renewable energy, okay, and there are those excess. So this is something what we try to address the blending of renewable energy, given that we can make the use of fossil fuel. Since this paper was introduced, many applications have been seen. People are using this technique to plan for renewable energy growth in different countries like New Zealand, Ireland, China, India, Nigeria, UK, more than now. Okay, but I don't have the time to go through those. Leave it to you to look up themselves. Okay, just type the keyword CHEPA. Okay, CHEPA means carbon emission pinch analysis. Okay, then you can find some of this interesting work. You can do it for your country, for your region, for your province. Okay, this can be done quite easily. Now, graphical method is always good. Okay, it gives you insights, it gives you the view how you can allocate the resources to the area that require those energy, but they suffer with accuracy problem. So we also developed some algebraic method, okay, similar to problem table algorithm in heat integration or cascade method in mass integration. You can do this using simple spreadsheet. Okay, young people like to use spreadsheets. Some old people, some professional planners, they still prefer to use algebraic method. Yeah, you can do that. Okay, that's the procedure. I won't go into the details. I'm showing you that the same case study that you do, if you plot it up into Excel. Okay, I actually uploaded this on the what we call a publisher page of my book. Anybody can just download and make use of the spreadsheet and punch in the value and it give you the solution. Okay, this is the Excel spreadsheet. Okay, it will give you the exact solution just like the one that we identified in the graphical method. That's the algebraic method. And if you are assuming the renewable does have a bit of CO2 emission, the same target as well, 1.042 million. If there's zero emission, then there's 830,000 terajoule of renewable energy. Those are methods that can be utilized. Okay. Very quickly, I jump from insight-based pinch analysis method into programming, since the majority of us here are very much into programming. I am not a hardcore mathematical programmer. Okay, I do self-learn optimization by myself. I started from pinch. Later on, when I learned superstructure, then I feel that superstructure is easy to do, but there's very little novelty. Okay, there are something called automated targeting. What we did was the same cascade that you see just now. We coded into programs. You can do it using GAMS, Lingo, even Excel solver. Okay, because it's a linear program. Once you do that, we can turn on Excel solver to solve this thing without iteration. Okay, that's the setting for solver. Okay, and you can just turn on solver. Solver can do the solution for you because this is a linear program. Of course, to get paper published, we tend to write very complicated equations so that the reviewer will believe us. And these are the mathematics that we have to show the reviewer so that they can publish it. But when you face the practitioners, facing the industry, facing government sectors, showing them Lingos and GAMS is chasing people away. Okay. In China, maybe different because many Chinese are very good in mathematics. Outside China, many people are very afraid of mathematics. Tell them that mathematics can do a lot of jobs. Thank you very much. We will think about it later. Okay? If you show them Excel, they say, oh, really? This can do it in a computer. Yeah. They are more willing to try if it is Excel based. Don't get me wrong, if you are doing high-end mathematics, make a simple interface in Excel. Behind that, we have all the programs and things can be done quite easily. Again, you can charge them high money, isn't it? Alright, anyway, those are things that you can do with Microsoft Excel as well because Solver does provide a good solution for linear program. The good thing with linear program is that you can even do cost analysis. While biodiesel cost is increasing, the model will tell you when you need to switch off the biodiesel usage and use other renewable better. Okay, so that's the analysis you can do with a simple linear program in the face of Excel spreadsheet. Finally, let me just draw your attention on two other important things. People are talking about CCS, carbon capture and storage. When we talk about CCS, that means that we capture CO2 from point source, power plants, petrochemical complexes, where they store it in those regions like underground storage. The challenge is to identify what techniques that we should use to capture CO2 and where should we store it. Okay? Of course, if you have superstructure, you can build this in a very complex superstructure and try to solve it. I tend to show people, in terms of understanding, very simple, because you have a composite curve. Now your CO2 is about 31.2. If I want to cut the CO2 by half, and your renewable is already maximized, unless every one of us stay on the tree, there's no way to generate more renewables. What we can do is install carbon capture and storage in the facility, capture the CO2, store it underground. Okay, and the problem with carbon capture is that there will be some amounts of energy losses because we are using amine absorption. You need to regenerate the solar. There will be some energy that is lost. That energy has to be compensated. Okay, you can compensate it with renewables. You can compensate it with some low carbon fossil fuel, okay, like natural gas, but those have to be accounted for. And once this carbon has been captured, you need to plan for the storage. Storage can go with the EOR, enhanced oil recovery, but then you need to get your storage ready. Okay, I'm showing you here versus CO2. The diagram on the left is two reservoirs that are ready. There are two power plants here. How do we get the reservoir ready for the power plant to store the CO2 is still a challenge. Sometimes your reservoir is only ready by 10 years' time. I'm really capturing CO2 now. What can I do with my captured CO2? Well, we need to store it somewhere else. Or else, why not put it under the Coca-Cola and then all of us drink it? That's CO2 storage. Are you willing to drink Coca-Cola with captured CO2? It's not an easy task. Okay? You can do that using programming. You can do it using superstructure. I'm still showing superstructure. So those are things that you can do. And also, you are also talking about the CCS for bioenergy power plant, because this is something that people are talking about lately, how to use negative emission technology. The concept is capture CO2 from the atmosphere back into a system, because bioenergy is carbon neutral. If you install CCS, you remove more CO2 than is released. So this is negative emission technology, something that is getting more and more popular in the okay? We did this work last 2 years with the help of some UK colleagues. British Council did sponsor us and develop some algorithm that, like I told you, we put Excel in front, we put Python behind, so that the industry guys will be happy to use our Python. So they just key the data and get answers from there. So finally, let me conclude that process engineering tools diverge. Again, I'm showing you graphical, I'm showing you automated targeting, all these things are tools that we can use to decarbonize our system, to reduce CO2. If you are keen to learn more about it, those are textbook, the main product produced during COVID. Okay, and I would like to acknowledge my partner Raymond Tan, who has been doing this CO2 with us for the past 10 years or so. We started with some very low-end thing. The conclusion is, if you want to, your generation, my generation, or next generation still live on this beautiful planet, we need to do something about it and more rigorously, bigger, full force. Or else we can have the next 4 PSE workshop in this Mars or Moon, right? You can now get a ticket to fly to the outer space, so not a problem. So moving to Mars or Moon for meetings is something can be done within the next 30 years. Okay, I'm sure we get to see it in 30 years from now. Finally, let me invite you to come to Malaysia for this Process System Engineering Conference, or Asia Edition. This is in August. The one for international will be in June in Florence. The Asian Edition will be